The brain inside your laptop was once just sand. That tiny chip, smaller than your fingernail, holds over 100 billion transistors, each one smaller than a virus. Together, they power everything from opening an app to streaming a movie. From raw silicon pulled from the earth to the screen you're staring at right now, the journey is nothing short of incredible. So it all begins with one of the most common elements in existence, silicon. It's found in sand, it's everywhere in rocks, and naturally you can find it in glass. But inside a computer, it's transformed into a much more powerful element. It's what gives electricity the ability to flow in just the right amount, not too fast and not too slow. It's this precise balance which makes silicon the ideal material to use when constructing tiny circuits. But not just any sand will do. The process starts by mining a special kind of rock called quartz. This quartz is heated to extreme temperatures over 1500 degrees Celsius until it melts down into pure silicon. And hey, when we say pure, we mean it. The final product reaches a purity level of 99.999999999. You get the idea, percent. At that level, even a single speck of dust could ruin everything. Once the ingot's ready, it's sliced into thin round discs called wafers, each one about the size of a dinner plate, but thinner than a credit card. These wafers are the foundation of every modern chip, the surface where billions of tiny components will soon be built. And from here, the real transformation begins. Before a single chip is made, it has to be imagined. Long before the machines get to work, engineers sit down and design the brain of the computer, a chip packed with billions of tiny pathways that carry information at lightning speed. That's where powerful software comes in. Using computer-aided design, or CAD, engineers map out these circuits down to the tiniest detail. Once the design is ready, it's printed onto something called a photomask, a clear glass plate that holds the blueprint of the chip's layout. Think of it as like a stencil, except instead of paint, it guides beams of light to carve microscopic patterns into silicon. This mask will be used again and again, layer by layer, to bring that digital design to life in the real world. And that's where the real building begins. Turning a design into a working chip takes place in an ultra-clean room, even more sterile than a hospital. Workers wear full suits and the air is constantly filtered. At this level, a single speck of dust can destroy an entire chip and cost thousands. With the silicon wafer ready, the first layer begins. It's coated with a light-sensitive liquid called photoresist, spread evenly like film on a camera. Then comes lithography. Using extreme ultraviolet light, the design is projected onto the wafer, carving out patterns just 2 nanometers wide, over 30,000 times thinner than a human hair. Machines built by companies like ASML handle this step. These massive tools cost hundreds of millions and use mirrors polished to atomic precision. And it doesn't stop at one layer. The wafer goes through this process again and again, building up dozens of layers to form a single chip. Step by step, the invisible becomes real. Once the pattern is etched onto the wafer, the real construction begins, and it's nothing short of incredible. Think of it like building a 3D city, only this one is invisible to the human eye. Roads, towers, bridges, all packed into a space smaller than your fingernail. The first step is etching. This is where special chemicals or plasma carve out tiny paths in the photoresist layer. These pathways will later carry electrical signals, just like roads carry cars through a city. Next comes doping, also known as implantation. High-speed ion beams shoot tiny atoms like boron or phosphorus deep into the silicon. This changes how electricity moves through certain areas, turning parts of the wafer into tiny switches and amplifiers. After that, it's time for deposition. Then layers of metal, usually copper or aluminum, are added to fill the etched paths. These metals create wiring that connects the billions of transistors together. And that's just one layer. To build a full chip, this process is repeated again and again, sometimes over 100 times. Each new layer adds more detail, more function, and more complexity. After months of building, each wafer is finally complete. But not every chip on it is perfect. Tiny imperfections, too small to see, can make a chip slower or less reliable. That's why every single chip goes through strict testing. Special machines check how well each one performs under different conditions: heat, pressure, speed, everything. Once tested, the chips are sorted by performance. This process is called binning. Some chips run faster, use less power, and pass every test. These become high-end models like Core i9. Others may not perform as well, so they're categorized as i7, i5, or i3. Once sorted, lasers carefully cut the wafer into individual chips. Each chip is then packaged with a heat spreader, a metal cover that helps manage the heat generated when the chip is working hard. From here, the smart ones move on, ready to become the brain inside your next laptop or desktop. Alright, so the brain's ready, now let's give it a body. Once the CPU is complete, it's placed onto the motherboard. That's like the skeleton and nervous system all in one, carrying signals, power, and data between the chip, memory, storage, and screen. Automated arms place hundreds of tiny components onto the board: resistors, capacitors, memory chips, each one perfectly aligned in just seconds. The board then moves through a high-temperature oven, melting the solder and locking everything into place. Next comes the screen. LCD panels are carefully installed, connected by thin ribbons of cable that link back to the motherboard. A built-in webcam and microphone are added before the frame is closed with a sleek bezel. Then, the bottom half of the laptop is built. Speakers, touchpads, keyboards, and cooling systems all come together. Gaming laptops get larger fans and extra heat pipes to handle intense performance, while Ultrabooks focus on staying slim and silent. With all parts assembled, the machine looks complete, but it's not quite done yet. Before any laptop leaves the factory, it's put through real-world testing. It's exposed to heat and cold, shaken to simulate travel, and pushed to its limits to make sure it doesn't overheat or crash. Machines check every key, every port, every screen pixel. After that, trained technicians run manual checks, making sure the screen is crisp, the keyboard feels right, and everything works exactly as it should. Finally, the laptop is cleaned, packaged with its charger and manual, sealed in a box, and shipped out, ready to land in stores, homes, and backpacks around the world. From grains of sand to machines that think, humanity has definitely come a long way. The next wave is already here. Chips are no longer just flat. Researchers are building quantum and brain-like chips that could change how machines learn, decide, and even create. But as we push the limits of science, one thing remains clear. The future of computing may look nothing like the past. If you enjoyed the video, make sure you hit subscribe for more stories behind the tech that powers your world.